Welcome, ladies and gentlemen, to our lecture on kinematics with constant acceleration. Recall that in our last lecture, we derived these equations as our kinematic equations for constant acceleration. And now that we have this shiny new tool for investigating motion with constant acceleration, when is it appropriate to use these equations? What kind of conditions must be met for us to apply these equations? So we may use these equations when acceleration is constant. So that gives us a couple situations where we can use this. One situation where acceleration is constant is in a system that's driven such that it has constant acceleration. So something that's pushed along at a constant acceleration. A good example of this is a car. So we can imagine a car's engine providing power that causes the car to move with constant acceleration. Even if there is significant air drag or significant friction going on, the engine just keeps supplying more power so that the acceleration stays the same for some amount of time. So that kind of situation can give us a system that has constant acceleration. Usually in this kind of thing, a problem will have to tell you that this happens at constant acceleration. The other kind of system that we could have is free fall. And remember, free fall is objects falling while affected by gravity only. So this is objects falling with no air drag, no friction, just the force of gravity acting on them. Now, for this to take place, we would have to have things in a vacuum or something like that so that there's no air to interfere with them. But we can also have systems where we're in the approximation of free fall. And all we require for the approximation of free fall is that air drag is small enough to be negligible. So we have something with enough density and it's falling a short enough distance that we can neglect air drag and our answer will only be off by a tiny bit. And this happens pretty regularly. If we're dropping a ball or a person going off a high dive or something like that. These kind of situations where we have a pretty dense object and they're not falling super duper far, we can have a situation where we can neglect air drag and we can come out with an answer that's approximately correct. So I want to take a second here to make a note about free fall and gravity. So note that when we have free fall, the acceleration due to gravity, little g, is equal to 9.8 meters per second squared. Now I want to make a distinction here and remind all of you guys that the force of gravity is not constant. The force of gravity is weight. And we know that this is not constant. We know that things have different weights. A bowling ball and a basketball have a different weight. Two people can have a different weight, right? A car and a dog have very different weights. However, the acceleration that gravity imparts on an object that's near the Earth's surface, that is constant, and that is little g. So, again, the force of gravity is not constant. That's weight. But the acceleration due to gravity is constant, and that is little g. So we know that it's okay to use these equations in systems that are driven so that acceleration is constant, and in systems where we have free fall or that we can approximate that something is free fall. So it's close enough to free fall that our answer will only be off by a tiny bit if we neglect air drag or friction. So how do we put these equations to work? The first thing to remember is that you get to choose the coordinate system. And I've said that many times at this point, but I always want to remind you guys that you get to choose the coordinate system, so choose it in a way that makes the problem easy for you. And what does it mean to choose a coordinate system? First, it means that you choose an origin. So you choose position 0, right? Or in 3 dimensions, in Cartesian coordinates, 0, 0, 0. So make sure that you choose an origin that's advantageous. Often I choose the origin so that x initial equals 0. But there are a lot of different ways to choose it, and every time you look at a problem, you should think, what's a good spot for the origin? And don't set it at some arbitrary place. The next thing that you get to choose is you get to choose a system for your coordinates. That's part of choosing coordinates. So what does it mean to choose a system? Well, usually in this class, we use Cartesian coordinates, right? Cartesian coordinates are x hat, y hat, z hat. These are really common because they're really good for describing things in 3-dimensional space, which is where most of our stuff takes place. But there are a lot of other coordinate systems, and we always choose a coordinate system that works for us in that particular problem, that makes it easy to describe things. For example, when we want to describe something that's a sphere, often we use spherical coordinates because the equations for a sphere are a pain in Cartesian coordinates, but really simple in spherical coordinates. Okay? And then we have other things like circular coordinates, cylindrical coordinates, things like that. So always remember that you're choosing a system as well. In this class, often we'll just default to Cartesian coordinates, but we are choosing a system when we choose that. The next thing, we choose a direction. And this is particularly important in Cartesian coordinates, and what I mean is we choose a direction for positive. So oftentimes we'll choose Cartesian coordinates for this class, and then we'll pick a direction for x hat that's positive. So if we move in one direction, we're moving in the positive x hat, and then when we move in the other way, we're moving in the negative x hat. And then because in our coordinates we're always choosing axes that are perpendicular to each other or orthogonal to each other, that will define what direction will become our y if we're in 2 dimensions. And then those two define our direction for z. In this case, z would be out of the page in 3 dimensions. But we choose how we're going to kind of align this thing. And what we generally do with this is align it to our physical system, again, to make the problem easy to solve for ourselves. So those pieces are all involved in choosing a coordinate system. The next thing we get to choose after our coordinates is we get to choose the correct equations. So to do this, we write down the variables that we know, we write down the variable that we want to know, and then we set up a system of equations that allows us to solve for the variable that we don't know yet, the one that we want to know. Remember that in algebra, we have to have the same number of equations as we have unknown variables in order to have a solvable system. And choose the equations so that you can use the easiest math possible to solve the problem. And then finally, to put these equations to work, we turn the crank on the math. So we pick a coordinate system, we list the variables that we know, we figure out the variable that we want to know. All right, we choose correct equations. Okay, and then we just solve. Solve math. Solve the system of equations that you set up for the variable that you want to know. That's all there is to solving these kinematic problems. So let's go over it by doing a couple of examples. So our first example here. Jim Bob makes YouTube videos. Today he has strapped a solid fuel rocket to his car to run a super speed quarter mile on the local highway. If Jim Bob's rocket-propelled car has a constant acceleration of 14.7 meters per second squared, or 1.5 Gs, how long will it take Jim Bob to finish a quarter mile? How fast will he be going when he finishes the quarter mile, both in meters per second and miles per hour? So, what do we have here? We have Jim Bob, and he's got a rocket strapped to his car. So let's first draw the problem here. We have Jim Bob's car here, and Jim Bob has put a solid fuel rocket on this thing. Okay? Maybe we have some flames out the back. So here's Jim Bob's car. And he's going to run an American standard drag race 1/4 mile. So here's the setup. So let's choose a coordinate system. The first thing I do, this is going to be one-dimensional. He's going to drive straight for this quarter mile. And I'm going to put the origin at Jim Bob's front bumper and put the x-hat direction in the direction he's going to go. This makes everything easy for me because all of my numbers are going to be positive when I solve this. So I do that. I have a coordinate system now. I have one-dimensional motion. I pick a one-dimensional coordinate system. And then I list the variables that I know. Well, I've set up my coordinate system so that I know that x naught, x at time 0, equals 0, because that's where I put the origin. He's starting from rest, so v naught equals 0. And I know that he's going to go a quarter mile. So x final is equal to a quarter mile. And while we're here, let's do a unit conversion. A quarter mile, there are 5,280 feet in a mile. There are 12 inches in a foot. And there are 39.37 inches in a meter. So the miles cancel, the feet cancel, the inches cancel, and we're left with meters. And this is 402.337 meters. So x final equals a quarter mile, which is 402.337 meters. And then our other known variable, we know that a is going to equal 1.5 g, which is 14.7 meters per second squared. So then what is it asking us? Well, first it asks us how long does it take Jim Bob to finish, so t equals what? And second, it asks us how fast he's going to be going when he finishes, so v final equals what? This is definitely going to be a one-dimensional kinematics problem. Again, the motion's in one dimension. He has constant acceleration, so I'm all good on kinematics. And the two equations that I want to use are going to be x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. So converting these equations to something that makes sense for our physical problem, putting in our variables, we know that x naught and v naught are both 0. So x final equals 1/2 a t squared. And that means that t equals 2xf over a. And this is the answer to the first question, right? What does t equal? It equals this. And then V final, again, V naught equals 0, starting from rest, equals AT equals A, and then 2xf over A in a root, which is equal to 2A xf. Okay, so V final equals 2A xf in a root. And that's the answer to the second question right here. We wanted to know how fast he was going. So for the first question, units, we have seconds on the left, we have a time, and then we have meters over meters per second squared, all in a root, and that equals seconds. So units check out. Sanity on this one. T goes up as xf goes up. So what does that tell us? If he was going further than a quarter mile, it would take him longer with the same acceleration. That makes sense, right? And we have t goes down as a goes up. So that tells us if he had a bigger acceleration, but was still only going a quarter mile, the time that it would take him would go down. Well, that makes sense too, right? With a bigger acceleration, he'll be moving faster at each point along the quarter mile, and it'll take him less time. So that makes sense. For our second answer, the units, we have meters per second on the left side. On the right side, we have meters per second squared times meters, all in a root. And this comes out to meters per second. So the units work. Sanity for our second answer. VF goes up as A goes up. So if he goes still 1/4 mile, his velocity at the end will be faster if he has a bigger acceleration. That makes sense. And V final goes up as XF goes up. So if he has the same acceleration, but he gets to accelerate over a longer distance, he'll also finish going a faster velocity. That makes sense as well. So we have two answers. Both of them check out on units and sanity. So these are the answers to this problem. And then finally, we plug in numbers at the very end here. So t equals 2 times 402.337 meters over 14.7 meters per second squared. All of that in a root. And that equals 7.40 seconds. Because remember, here we have three significant figures, so I've done sig figs in the answer here. And 7.4 seconds is a blazingly fast quarter mile, as expected for Bob's rocket-propelled car here. For VF, we have 2 times 14.7 meters per second squared times 402.337 meters. That's all in a root. And that is equal to 109 meters per second. And then the question also wanted to know in miles per hour. And that's just a unit conversion. So that unit conversion is 108.76. I'm carrying extra digits here than my significant figure answer from before. Meters per second. 39.37 inches per meter, 12 inches in a foot, 5,280 feet in a mile, and then 60 seconds in a minute, 60 minutes in an hour. Okay, so meters cancel, inches cancel, feet cancel, and we're left with miles. The seconds cancel, the minutes cancel, and we're left with hours. So we have miles per hour now. And this is VF equals 243 miles per hour. So moving on to our next example here, this is just a second part of the prior question. Jim Bob is a lot of things, but one thing he is not is a rocket scientist. Once you start a solid fuel rocket, there is no off switch. It stops when the rocket runs out of fuel. What if Jim Bob's rocket causes him to have the same constant acceleration for half a mile? How fast will Jim Bob be going at the end of a half mile? So remember, our answer for how fast Jim Bob was going at the end of the quarter mile was V final equals 2 x final times A in a root. So we can use that to solve this problem. So now we want to know at a half mile. 1/2 mile equals 2 times 1/4 mile. So XF goes to 2 times XF. We're going to go twice as far. We can plug that into our answer from before because we solved it with variables. We have 2XF instead of XF. And let's rename VF. Let's call it V sub 1/2. So his velocity at the end of a half a mile, or his speed in this case, because we're just looking at the magnitude, the speed at the end of a half a mile. And now we have this for it. And then if I want to pull this 2 out of here, I would have root 2 times 2 XFA in a root. And that would be equal to root 2 times VF, right? His speed at the end of the quarter mile. So his speed at the end of the half mile is root 2 times his speed at the end of the quarter mile. So our answer expressed in variable form here as a function of the variables that we know made it really, really easy to answer this second question. And again, we can give this one now really easily in terms of meters per second and miles per hour. We don't have to do a bunch of new unit conversions or anything like that. All we're doing is multiplying root 2 times our answers from before. So remember before, we have root 2, and our answer in meters per second before was 108.76 if we carry extra digits beyond significant figures in meters per second. And that gives us a new speed of 154 meters per second now when he finishes the half mile. And in miles per hour now, we have again root 2, and then we multiply it by 243.289 miles per hour now in our miles per hour unit. And this one gives us a speed at the end of the half mile of 344 miles per hour. And physically, what these speeds tell us is basically Jim Bob's car is probably going to be coming out of the seams long before he gets to a half mile if he's got a rocket that can put this kind of acceleration on his car. So now let's do a different example. Here's a whole different problem. Cool James is the pitcher on his Little League team. He can throw a baseball 55 miles per hour. If we neglected air drag, what height would we have to drop a baseball from for it to be moving at 55 miles per hour when it hits the ground? If one story is 3.1 meters for hotels and residences, neglecting air resistance, on what story am I risking hitting someone in the head with a baseball moving 55 miles per hour when I drop it off the lanai? So this one is two parts. This first part is one problem, and then the second part is a little tag question like we had with Jim Bob, where we answered the thing, and then we have the tag question, how fast is he going at the end of a half mile? So the first part, I have a baseball, and I'm going to drop it some distance where it hits the ground. And when it hits the ground, we know that V final equals 55 miles per hour. So let's go ahead and do the unit conversion while we're here. 55 miles per hour, 5,280 feet in a mile. 12 inches in a foot. 39.37 inches in a meter. $60 minutes in an hour. 60 seconds in a minute. The miles cancel, the feet cancel, the inches cancel. We're left with meters on top. The hours cancel, the minutes cancel. We're left with seconds on the bottom. So we're going to have meters per second. And this is equal to 24.587 meters per second. So we know that V naught is going to be 0. We're dropping it. We're not throwing it at the ground. So it's starting from rest here. And then I'm going to choose a coordinate system at the bottom of the baseball for the origin that goes down, again, because all the motion's going to be down. And then I know that I'm going to reach X final, the ground, after I travel this distance. I'll be X final away from the origin. And the question is, what is that distance if V final is 55 miles an hour? And I know that A equals little g equals 9.8 meters per second squared because we're neglecting air drag. So I'm going to solve this with 1D kinematics and the equations that I want to use. I'm going to use just the basic ones again. X naught plus V naught t plus 1/2 AT squared. And I'm going to use V equals V naught plus AT. And again, I've set up my coordinate system so that X naught and V naught are 0. So I have X final equals 1/2 GT squared. I know G, X final is what I want to find, but I don't know T yet. My other equation, V final equals GT. Again, V naught is 0. And this one tells me that T equals V final over G. So then X final equals 1/2 G. And then I replace T with this VF over G squared. And then I have 1/2 VF squared over G. So X final equals VF squared over 2G. My units on this I have meters on the left. That equals meters per second. Meters per second. And that's squared, that whole quantity. And then that's divided by meters per second squared. So the square goes in, and the seconds and seconds squared cancel. The meter cancels just one of these, and I end up with meters. So the units work. For sanity, XF goes up as VF goes up. So if I have the same acceleration due to gravity and I want the ball to have a higher speed when it hits the ground, I have to drop it a further distance. That makes sense. I have XF goes down as G goes up. So if I had a greater acceleration due to gravity and I was going to drop it and have it reach the same speed, I would have to drop it a shorter distance because now it has a bigger acceleration. That makes sense. So you can see the behavior of my equation matches the behavior that makes sense in the physical world. So then if I plug in these numbers, I have XF equals VF, which is 24.587 meters per second, squared over 2 times G, 9.8 meters per second squared, equals 30.843 meters. And you can see this time we have just two significant figures on both of our input variables. So this is 31 meters. So now we've answered the first part entirely. We have the distance expressed in terms of the variables we know, and we also have a numerical answer for the distance. It's 31 meters. If we drop a baseball from 31 meters up, it'll be going about 55 miles an hour when it hits the ground. And so then we go to the second question. If one story is 3.1 meters for hotels and residences, neglecting air resistance, on what story am I risking hitting someone in the head with a baseball moving 55 miles per hour when I drop it off the lanai? So if I model this one, and I'm standing up here, and I drop the baseball, and then it lands on someone's head, you can see it doesn't quite have to make it to the ground, but if I'm dropping it from shoulder height, the difference between just having it drop from here to the ground and from shoulder height to someone's head, it's not very big. So let's forget about that and say it's just this distance. It's just the 31 meters. And then we just have a unit conversion, basically. So my unit conversion is 31 meters, and there's 3.1 meters per story. So that equals 10 stories. So the answer to this second part is that I'm risking hitting someone in the head with a 55 mile per hour baseball if I drop it from 10 stories up. So those were a couple examples of using kinematics with constant acceleration to do some back of the envelope calculations. Your homework for today is going to let you practice this skill some more. And next time we'll generalize to solving these same kinds of problems with constant acceleration in multiple dimensions.